Good morning, everyone. This is indeed the lecture on implementing reduction. Are we all in the right place? Now, this is the first in a series of 39 talks on implementing reduction, which together make up the second largest in a longer series on iterative operations, that is, reductions, scans, window reductions, partitions, and inner products. So today, I will just be gently bringing you up to speed with kind of the landscape of reduction. Now, here's a reduction. We're not particularly interested in this kind of reduction because it's not very hard to do. We're more interested in large reductions. When a programmer types an absolutely huge array in APL and wants to reduce it, we want that to be fast. And when I say fast, well, many people say they wrote some fast code because they don't know how to make it faster. When I say I want code to be fast, I say I want it to be fast as it possibly can be. It's as fast as the CPU can even execute instructions. Preferably, it's as fast as the CPU can read memory from the workspace. So the only way to make it faster is by getting faster RAM. First, I'm going to talk about, so of course, we have general code which takes any function and reduces along an array by selecting elements in turn and applying that function, and so on until it gets a result, and then it puts that result as one element of the result. What I'm interested in are the special cases, particularly for primitive reductions, and these will all be on flat arrays. So whenever you do a reduction, there are a number of steps that APL takes. Of course, first it checks for a left argument, checks for a trivial case. It then represents the shape in a particular way, which we'll talk about next. And then it tries a bunch of special cases. So we have 2,000 lines of code for implementing reduction that deal with all sorts of reductions, sums, all these different Boolean reductions, products, min, max. And these are all checked as cases. We attempt to apply this special code before going into the general case. So this talk is mainly about these two sets of reductions. Reductions on Boolean arguments and reductions on integer arguments with the operations that can be done quickly. So as opposed to like GCD, which requires, the actual GCD operation requires so much time that the operation itself is the main cost in reduction. With much faster, better supported functions like addition, subtraction, max and min, these have vector support on the CPU. So you're able to do this reduction as fast as possible, limited only by memory. So we're most interested right now in talking about these particular reductions. But first, some background that's essential to any sort of reduction is knowing how reduction sees its argument. Now, of course, the argument is an array, and in addition to this array, there's an axis which you're reducing along. So you can specify the axis either by putting a bar or not on the slash that picks the first or last axis. If you want an axis in the middle, you can use the brackets to specify an axis, or you can use slash bar with a rank, which reduces the size of the cells that are operated on, and so specifies a middle axis. However, regardless of how many axes there are in the array, reduction only cares about, in a sense, 3 axes. It always sees an array with 3 axes. So here I put up an example of a rank 3 array. I've kind of squished the cells together, but you can see there are 3 axes, which I'll call the leading axis, the reduction axis, and the trailing axis. So if you have a rank 3 array and you reduce along the middle axis, this is the kind of reduction you get. But in fact, every reduction actually reduces this to something that's the same as this. Because if you have many axes before the reduction, it doesn't matter the the particular array structure of the cells, all that matters is how many cells there are. You're still going to do a reduction on one cell at a time, so we only care about how many cells there are, which means we can combine all the axes before the reduction axis into one. And similarly, for the trailing axis, when we're reducing, the way I typically think of this is as combining one row with another. We only care what the length of each row is, the number of elements it has, rather than what its shape is. So one of the first things we do to execute a reduction is we transform its shape into this set of three axes. So if I want to do any reduction on an array which has shape 4, 2, 5, 7, and I'm reducing along this second to last axis, that axis stays the same, and the other two axes, I take the product, and I only consider the total length that's the product of those axes. And this applies even if there are no axes before and after the reduction. In that case, the length is just 1. Actually, the most common case is probably reducing a single vector. And in that case, there are no axes before the reduction and no axes after the reduction. So we have a leading axis of 1, we have a reduction axis, which has whatever length the reduction has, and we have a trailing axis, which is 1. And sometimes I'll also pronounce this as being stride 1. The stride is the distance between elements that are combined with the reduction function. So when you combine rows of length 2, say, the function acts on elements that are 2 apart. When you're doing a reduction simply on a vector like this, the elements that you're combining are 1 space apart. So here's the general model. We take our shape as input, we do some multiplication, and we get a shape as output, which is always exactly 3 elements. And that means that for the rest of the reduction code, we don't have to worry about having a variable length shape, which is something that can slow down C code. We're able to work with just 3 particular lengths, and that allows our code to be very static and to not change depending on what the input array looks like. However, of course, we're going to use this shape to select from various algorithms. When we're selecting an algorithm, what we care about is actually not the length of each axis, but we care about the size of the cells that these axes imply. So to get these cell sizes, we're going to perform a reverse multiplication scan on the 3 lengths. This is perhaps an argument that the axes should be written in the other order, that we have to reverse this scan. But that transforms us from axis lengths into cell sizes. So we can say, if the stride is 7, the trailing axis is 7, we are reducing rows of length 7. We're combining rows of length 7 together. If then the reduction axis has length 20, each reduction works on an array of size 140. And finally, if there are 5, the leading axis has 5 elements, there are 5 independent reductions, the entire array has size 700. So the reason we work with these cell sizes is because in order to write fast code in the sense that I mean, the fastest the processor can do, you have to work on sufficiently large pieces of data. You need to work at least a vector register at a time, or you're not getting the full power of the CPU. Because the CPU can do many operations at once, but the only way to do that is to combine all the arguments to these operations into vector registers. So we end up with these cases, and these are going to mirror the cases that we go into as we search for code that's best to reduce our particular array. The easiest case is the long row case. In that case, we can simply take rows of the array and combine them together with our reduction operation. It's slightly harder if these rows get short, because combining 2 rows together has more overhead, and you can't necessarily split a row up into vector registers evenly. You may have a partial vector register at the end. And as the rows get shorter, that cost both to start a row and to deal with partial vectors gets higher as a portion of the total time. And you stop running at the full vector speed. So we'll need other tricks to deal with large cells. As the cells themselves get small, we have to perform the reduction on the entire array. So we need to find some way to pick a chunk out of the array that's even larger than a cell and perform a reduction on that. And that's something that's very tricky. That's something that currently we only have working for a few Boolean operations. So as we go down this list, the algorithms here get very difficult. And I'm going to kind of move in this direction. And we won't see everything APL does, and APL doesn't do all that it can do. So reduction is a very deep operation. There's a lot to know out there. There's a lot that I think hasn't been studied by anyone that's not understood at all. Here's the simplest case. If your array has long rows, actually much longer than I've shown here, then the reduction just reduces to combining rows together. So I take the first row, and I put it in my result. I take the second row, in this case I'm doing the max operation, so I take the max of that row and the current result, and put it there, and so on. And this combination can use vector instructions because each row is very long. So what we can do is, rather than moving one element at a time, we consider how many elements fit into a vector register. Maybe it's 4, maybe it's 8. And to combine rows, we pick up 4 elements from this one, 4 elements from this one, put them together, put them in the result, all at once with a single vector instruction. And we keep doing this until we've reached the end of the array. And you can see each result is the largest number that was in that column. Let's take a look at the performance here. So the graphs that I'm going to use, for the x-axis, I have the stride, the length of the trailing axis, the size of the rows that we're combining with the operation, and the speed in gigabytes per second. So for context, copying memory from one location to another runs at about 30 to 35 gigs a second, which, interestingly, is about the same speed as the reduction here. So reduction is going as fast as I can read and write data, which is very good. It could potentially be faster because it doesn't need to write the result for each row. It could potentially move at the speed of reading each row rather than reading and writing, which would be somewhat faster. But this reduction is very fast, and it's very close to the limit of the CPU what the CPU can do. That's the case at large strides. At strides over, I think, 500 is about the cutoff here. Let's take a look at the case for smaller strides. Ooh. Ah. Well, the stride 1 case is good. The stride 1 case is handled with a different algorithm than I've shown there. And it's actually running at, it doesn't write intermediate data. So you can see there's a little advantage when you can run at as fast as the CPU can read data, as opposed to as fast as it can read and write. But that's pretty small compared to the huge gulf that we get here. Now let's look at how min-reduce worked in Dyalog 17.1. This is what I consider a failure of the C language, because what we wrote is very straightforward code to do what I showed. We didn't explicitly vectorize it, tell the CPU to use vector instructions, but we used the way that you write minimum and maximum in C that I would expect the compiler to understand and turn into vector instructions. It didn't. So you get this, this very poor performance. It's over 10 times slower than what we were able to do using explicit vector instructions. On the other hand, the way that we use vector instructions in version 18 is that we have a lot of functions that implement that operation, say it's min here, on various types. And so we read from an array of functions, and then we call that function, which leads to function overhead. It does have a huge advantage in that we can change the array of functions at runtime. So when we start up APL, we check, does this CPU have AVX2? And if it does, I'll fill in that array with AVX2 functions. But it gives me this overhead. So while the 17.1 solution is generally pretty slow, at very small strides, where the operation is dominated by the per row overhead, it does better because there's less overhead. And if we were to very carefully rewrite this, so it's using a combination of vector instructions and scalar instructions, and all our loops are carefully arranged so that we do few branches, we could probably do at least as good as either of these, and probably get up to a vertical line there that's doing as well as the good vector reductions here. That's not what we're going to do. We're going to do this. So, in Dyalog 18.0, the performance is just like a flat line, which is, when you're doing performance stuff, flat lines are the best. Very, all the way straight. How do we do this? It's only possible for certain functions. We're going to need some mathematical properties of our functions in order to do this, because we're going to rearrange the way we do this reduction. So first, we need our operation to be associative, meaning that as long as we keep all the elements of the array in order, we can combine them in whatever order we want. So an example of an optimization that you can do with associativity is to rearrange this very deeply nested structure into a less deeply nested tree that combines two elements at a time. And this is the kind of optimization you would do if you're implementing something like MapReduce, which performs a reduction using many CPUs. We're not going to do this kind of optimization here. And we'll need actually an additional property. We'll need our operation to be commutative. So not only can we reorder the way in which reductions are performed, but we can also reorder the way that they choose their arguments. So here's an example of a different ordering for the reduction that would work better on a vector machine, because you can repeatedly take two halves of a vector, combine them together, take halves of that, combine them together, and so on. So this optimization that I'm going to show you works for operations that are associative and commutative. And fortunately, that includes addition, subtraction, multiplication, max, and min, all of the operations which are fast on vector registers. So what is the idea behind this operation? The concept here is actually to split up the reduction. Here we have a reduction with a small stride, and this can be actually any stride. You want a small stride because if the stride is long, as I showed, the reduction is fast. So we have a small stride and a large reduction axis. And what this algorithm is going to allow us to do is sort of push size from the reduction axis towards the trailing axis so that we can use this fast vector reduction. The way we do this is to split up our array. We think of it as an array with not 3 but 4 axes, or maybe we just first we move part of this middle axis into the first axis. Or no, we move part of the middle axis into the last axis. So we're going to do 2 reductions, and the first reduction takes a stride which is longer than our actual vector stride. It's a multiple of this stride. So here we say we're splitting a length 800 axis into 50 by 16, and the actual effective stride is 5 times 16, which is pretty large. And then we're able to efficiently do a reduction there. And now we obtain an array that's not actually the size that we want, but we can do one more reduction to get the final reduction result. So rather than doing a single reduction, we do one reduction that's efficient and one reduction which is not actually as efficient, but which is small overall. And this gets us our result efficiently. But it does involve reordering the operations, because changing a reduction of stride 5 to one with stride whatever 5 times 16 is, means that rather than combining elements separated by that stride, we're first combining elements that are further apart. Here's an animation of this reduction in action. We have here a something by 3 array. And what we're going to do is we're going to repeatedly double the last axis, double the stride, conceptually. So here I'm going to rearrange this array so that it's now a something by 6 array. And actually, this algorithm works even if the reduction axis is not evenly divisible by 2. So we'll see later that we can actually handle a partial last row. This combination that I did here, in memory, the array is all laid out in ravel order because memory is linear. So this is just a conceptual change to the way we think of the array. We don't have to move any data around to make this change. We do this again. We double the last axis and have the first axis. And now, well, actually we don't yet, but if we do this on an array enough times, eventually we get the rows long enough that reduction will be efficient. And now what we do is first we take the second to last row and put it in our result. Then we take the last row and combine it with that. Now, as I said, this operation is going to be commutative, but I'm going to keep track of the ordering as I'm doing this, because I can actually use the exact same code for reductions that don't use this special method, that are just using the long row case that I showed, just by skipping the step where I lengthen the stride. So I'm going to keep track of what order I'm combining everything in here. Then after that, I'll merge in the next row that hasn't already been seen. I'll do that again. And now I have the maximum of this reshaped array, even though it's got a partial last row. Now I need to do the second step, another reduction, which combines this back down to the final size. So I'm going to split this row in half and combine the second half with the first. And do this again. And finally, I get a result of length 3, which is the right length. That was our original row length. And if I compare this to the original matrix, you can see that each result is indeed the correct maximum. This first column has a maximum of 11, the second has a maximum of 12, and the last has a maximum of 15. So that's how we get that incredible flat performance for a large matrix, even if it has small rows. We're not done, of course, but for commutative and associative operations, this has allowed us to kind of extend our reach from working just when the last axis is long to when the last two axes together are sufficiently large. Let's look at Boolean arrays for a moment. So again, some Boolean operations are associative and commutative, some are not. And in fact, in contrast to when we're working with integers, the Boolean operations, there are Boolean operations which are not both associative and commutative, but which are fast to run. So we can see here are all the operations. These are pretty weird reductions. I wouldn't expect users to use them often. I still wish they were faster, but I don't think it's a huge impact to have them be slow. But we can see from measuring these are the timings when you can't use this operation that I showed. And I applied this optimization and said double the stride until it's at least 64 bytes with equals and not equals. And I got these timings. So here, the speed, there's another consideration as well here, which is that with Booleans, you can only combine rows quickly if both of them start at byte boundaries. And that means to do a fast reduction, the stride has to be a multiple of 8 bits. So the fact that we're doubling the stride each time is very good, and we can just make sure, in addition to this absolute limit on the length of each row, we can make sure that the length of each row is a multiple of 8 bits. And you can see here there are some spikes where in the non-combining case, where you get multiple of 8 rows. But actually there's also a very strange phenomenon, which is for equals and not equals, there are dips where there are multiple bits of 8 rows. So these dips are actually an indication that I have set my row limit wrong. And I was able to fix this just by increasing the row limit. So you see, when the row limit is too small, you get several artifacts. You get these slow runs as the size of the row, the final size after you double it enough depends on the initial size. So you get one run for each number of doublings that you do. And if the runs are still kind of increasing in performance, that means that you could still improve by doubling more. You haven't doubled it enough. And you also get these dips at multiples of 8, where it's saying, well, I should be doubling since it's not a multiple of 8. But multiples of 8, it doesn't do that. So they actually perform worse, which that should never happen. Multiple of 8 row lengths should always be at least as fast as odd row lengths. So when you increase the stride, you get this much better flat performance. Now, for associative and commutative operations, that's about as good as you can do because we're getting pretty close to the limit of how the CPU can do here. So we'll move. Maybe I should talk a bit about shortcutting. As you can see here, and an OR, which are also associative commutative operations. So they could be just as fast as equals and not equals. But in fact, I've done a considerable amount of work to make these, even with strangely shaped arrays, take shortcuts. So the thing about these reductions is that if you see a 1 or a 0, at that point you can stop the reduction. And we get this performance not by making the CPU analyze data faster, but by making it actually look at less data. It stops early. So here's an example of a reduction with OR. This is a reduction that can be shortcut. The result of OR, of course, is just 1 if there's any 1 in a row, and 0 otherwise. However, to figure out whether there's a 1 in a row, all we have to do is start looking across the row and stop whenever we hit a 1. So the only data that OR actually needs to analyze is this far into the array. It can stop as soon as it hits 1. So in the stride 1 case, you can see it's pretty easy to work with an array, to move along an array and stop when you hit a 1. Now, again, due to screen size constraints, I've actually shown a case here where shortcutting is not profitable because each of these rows fits in a single machine word. So you could check whether there's a 1 in the row using a single instruction. There's no need to stop early, and in fact, it would be detrimental to try to do any stopping early because that would cause problems with the CPU's branch predictor. But for very long rows, stopping early is essential because if we don't stop early, if we examine the whole row, we're possibly doing asymptotically worse than we could by stopping early. We are examining the entire array when if there's a 1 at, say, if there's always a 1 at maybe the 10th position, we can always do a constant amount of work. So that's an example of an algorithm that's particularly valuable for vectors. Another thing that I want to mention on vectors, which recall is the stride 1 case, is sort of a modification to our associative commutative algorithm, which, as I said, we're doing a little better on the stride 1 case because we're not reading and writing data, but just reading it. We can still do this whole doubling strategy, except when we start at a stride 1, we know that by doubling, we'll eventually hit exactly the length of a vector register, because vector registers are always a power of 2 length in bytes. So rather than doubling until we have a really long row, and reading rows and writing rows, and so on, we just work entirely in the CPU, never writing anything to memory, and we keep a single vector register. So, for example, with AVX2, 4 doubles form a vector register. So here I could read a vector register, combine it with another vector register, combine it with another vector register, and each of these combinations is maybe 3 or 4 instructions. And the latency is even lower because they're not dependent on each other. So this combination is very fast. And then finally, when I get to the end of the reduction, I can do this repeated splitting the register in half and combining it with itself. And finally, I get a single number for the result. Unfortunately, in APL, we can't actually do this. We can't do summation this way for floating point data. The reason for that is that addition is very difficult. So the problem with floating point addition is, in fact, that it is not associative. It is commutative. Adding A to B is the same as adding B to A. But if you perform the addition in a different order, because floating point addition rounds its result, you may get different answers by changing the order. So if you add a large positive number, then a large negative number, and then a small number, those two at the beginning are going to cancel out, and you'll see the small number. If you do it the other way around, if you add a large negative number to a small number, the floating point format will round because it only has a certain number of digits of precision. And then this sum will be rounded to exactly -1 times 10 to the 20th, and the resulting sum will be 0. So in general, it's really difficult to figure out what order you should add an array to get the most correct result. But for us, the ordering is already specified because APL reductions are defined to go from the end of an array to the beginning. So we have to follow that order for floating point additions. And we can't make any changes. Sometimes it's better than going left to right, sometimes it's worse. In particular, it's always different. Well, not necessarily always a different result, but it gives different results from doing this one vector at a time addition, which adds essentially with stride 4. So I can't make this optimization for floating point numbers. Integer addition is also difficult. This is a less fundamental difficulty, but it is something that you have to be aware of when you're implementing integer reductions. When you sum an array, the addition can overflow So you have to be careful to increase the type as you're moving so that the type is sufficiently large to fit the result. So where are we now with addition? These two red squares indicate this fundamental difficulty in floating point numbers, where we are not allowed to reorder the reduction. Otherwise, we're doing okay. The integer case, I have not yet implemented this stride doubling for the integer case, just because it's difficult to write the code for this. Another problem is that, well, one thing I could do when I write the integer algorithm is to use a facility we have in our vector operations, which is that we can run them on two inputs, not knowing whether it will overflow. And it will, if it encounters an overflow, stop and tell us. For a reduction, I can't yet make use of that, because if I do this reduction and it tells me that it's overflowed, I was doing the operation in place. I was updating a row as I went across the array. Then I've already written some of the data, and I would have to find a way to go back and redo that. It's possible, but difficult. So I think eventually that case will be optimized. The floating cases will not, because we have to go in this particular order. And if there's any way to reorder the floating point reductions for a higher performance while keeping exactly the same results, it's not known. No one knows how to do that. However, there is something you as a programmer can do, and this is going to be an optimization that's in version 18. And that's to, rather than writing a sum, this is for sums in particular, rather than just any associative commutative operation, you can replace your sums with one base. So evaluating in base 1 is the same as summing, because every place value is the same. It's just 1 to some power. So if you write this, then we have no obligation to do the sum in a particular order, and we can use these faster algorithms. And you can even reduce along any axis using the rank operator. So this is an optimization that will be in 18.0. It's a nice thing to know about. If you really care about floating point performance, and this is not performance at the cost of precision, by the way. This is actually typically a more precise ordering, because rather than combining one thing with another all the way until the end, it splits it into separate rows, which leads to smaller intermediate results, which gives you a little less rounding. So one base is actually going to be faster and more accurate than summation, usually. All right. Talked about summation a little. It's difficult. So rather than talking about things which are very difficult, I'll spend a little bit of time talking about the frontier, which is actually composed of working on things that are easy, which we hope will be able to apply the same techniques to things that are hard eventually. So this frontier is the Boolean operations. In the case of reduction, Boolean operations are interesting for a lot of reasons. The first is that actually there's a much wider gap between an unoptimized Boolean operation and an optimized Boolean operation. An unoptimized Boolean operation works one bit at a time, which is something CPUs are particularly bad at. An optimized one works an entire word or even a vector register at a time, which is a huge multiple over that one bit. Second, there are a lot more possibilities on Boolean reductions. We will have time to get to at least one of them, I think. There are more possible operations. And also, optimizations are typically easier to implement because you're working with single bits rather than entire numbers. And so one thing that I think will happen is that we'll be implementing all the really crazy new algorithms on Booleans, and we'll gradually extend these algorithms so that we can apply the same sort of techniques on integers and floating point numbers. Now, here's the performance of OR reduction. And this probably looks like a mess to you, but I say that it's in fact perfectly ordered. So it's astonishing how well this fits the model, I claim. So at the far right here, we have the case that I talked about, which is a search across each row with a shortcut. And the shortcut case for or reduce, I've made an array of all ones, and the non-shortcutting case, I've made an array of all zeros. So shortcut stops as soon as possible, and it's very fast. It just keeps going up. No shortcut is still pretty fast. These cases are all completely branchless, and they don't depend on the data at all. So you can see I have graphed 2 lines, but you can only see one of them because the operations are so consistent. It does exactly the same thing, which means that you get pretty much exactly the same performance. And there are 3 different cases. It looks like I just took a marker and drew squiggles everywhere. But this case at the top is fit with only 2 parameters. This case, the second case, is fit with a single parameter. And this last case is also fit with a single parameter. So if you have just 4 numbers, you can describe the entirety of Boolean performance on low strides, except for these 2, which are special cases individually for these specific numbers of bits. Actually, the stride 1 case, stride 1 reduction, not a stride. What is? Oh, this is not the stride. These are all stride 1 reductions, sorry, and this is the row length in bits. A reduction with a reduction length of 1 is just the trivial case. So you can see at the far left, that's the performance of the CPU just copying data. All right, so to just give you an overview of the 3 algorithms, these 2 at the top are both translating the or reduce operation to an equality test in the CPU. This one at the bottom, I don't think we'll have time for. This is a really interesting algorithm. The way it works is by fitting as many rows as it can into a single machine word, 64 bits. So the performance is entirely determined by the number of bits that you get in that machine word. For example, if you have rows of length 7, then you can fit 9 of them in a machine word, and that gives you 63 bits, all but 1. So the 7 case here is pretty close to the top performance. The worst case is 33 bits, which is about half of the top performance. So how do we use comparison to implement reduction? As I said, or reduction on a row is 0 if it's all zeros and 1 otherwise. Similarly, comparing to 0 on an integer gives you 0 if it's all zeros and 1 otherwise. So we can look at what's the performance of or reduce compared to actual comparison, and we see they're very similar. So here I've done something crazy to convert the Boolean array into an equivalent integer array. And these integer comparisons in version 17, I did a lot of work to make comparisons use vectorized operations, so I'm able to use those and go very quickly through the array. If the row length doesn't correspond exactly to a 1, 2, or 4 byte integer, then instead of using vectorized operations which pack many integers into a vector register and compare them all at once, I need to read them one at a time from the array. So I read a row, get rid of, I can't read, of course, 3 bytes at once. I can read 4 or 8 bytes at once, so I'll read probably 8 bytes. Get rid of the bytes that I don't want, compare it to 0, store that result, and so on. So that's why these spikes are slightly poorer in performance than the vectorized operations. I think I have to stop there. Any questions? Come on up.